Here are 4 versions of a velocity time graph for a falling object with air resistance. To find the distance travelled, we can add up small sections of area as we've seen before, but this is the first time that we acknowledge there's more than one way to do this. The top left green graph is the one that we've seen before, but we could do the approximation using rectangles above the curve rather than underneath, and they'd be formed using the value of the function at the end of the small time interval rather than the value of the function at the beginning. We could use rectangles based on the value of the function at the midpoint of the time interval. Or we could stop using rectangles altogether and use trapezia. In this case, the trapezia model the curve so well that you can't even see the deviation from the curve, so we'll remove the curve for a second to allow you to see it. Now we can write some maths down formally, but it doesn't change what's going on. We're just adding up small rectangles in different ways, or trapezia. We'll do it for 3 of the cases by looking at just one of the small time intervals of duration delta t, so that's a time interval from t to t plus delta t. For the green areas, we look at the value of velocity at time t, and for the yellow areas, we look at the value of velocity at the midpoint of the time interval. Now the time interval is delta t, so half the time interval is a half of delta t, and therefore we're looking for the velocity at time t plus delta t over 2. For trapezia, we're also looking for the velocity at the midpoint of the time interval, but because of the shape of a trapezium, we can write that another way. Here's a trapezium. If we draw these lines in, we can see that the 2 shaded areas are equal, which means that the area of the blue trapezium is equal to the area of the rectangle formed by the black outline. Where do we have to draw the horizontal black line to make that true? Well, halfway along, in other words, at the midpoint of the time interval, provided the slanted line is straight, which it is on a trapezium. Now that means, for example, that if this trapezium were part of a velocity time graph, like in section 1, the distance travelled, the area under the curve, is the same as the distance it would have travelled if it had been going at a constant speed equal to the average. Now that statement is generally true, but the important thing here is that the average speed is halfway along the time interval and halfway up the slanted portion of the trapezium because the line is straight. So we can write the velocity halfway along the time interval as halfway between v of t and v at t plus delta t, this midpoint here, and that's just the average of the 2 velocities just mentioned, v of t plus v at the later time divided by 2. Now what's the point of all that? Well, here's the important thing. If we're adding green rectangles, the height of the rectangles is given by the velocity at time t. If we're adding yellow rectangles, the height of the rectangles is given by the velocity halfway along the time interval. And if we're adding trapezia are just like rectangles, where the height of the rectangle is halfway up the slanted portion of the trapezium. But importantly, in the limit as delta t goes to 0, they all give correct answers equal to the integral of the velocity. And that's true when we're in the limit of delta t going to 0. Now for numerical integration, we aren't in that limit. Numerical integration strikes a balance between wanting your time intervals to be as small as possible for accuracy and wanting to not have an enormous amount of calculation to do. And that's why there's more than one technique or algorithm for numerical integration.